Welcome to a lesson with Dr. Powell. In this video, we're going to look at an optimization problem, application problem in calculus. We're going to try to find the length we should have of each side of this rectangle that has square footage given, so 100 square feet. So that given area, what should these dimensions be of maybe a fence or a boundary around that region so that it minimizes the cost of building it if it costs $5 per foot on these lengths and $9 per foot on these lengths? Okay, so how are we going to do that? We first realize, what are we trying to minimize? We're trying to minimize cost, which means cost should be the output or the y value of the function we want to minimize and do calculus on. So our function should represent cost. Okay, so, and it should depend on, what is it going to depend on? Looks like it's going to depend on x. We're going to determine what x value will minimize that cost. And from that x value, we can actually figure out what the length of all the sides are. Especially since you know that the area of the rectangle is 100, we should be able to figure that out. Okay, so beginning on, let's see, we need to find a function for cost. Well, let's see. The cost of building this side is $5 for each foot for x feet. Well, the cost of building this side is 5x. Okay, let's see here. Let's just make sure I got this going here. It's 5x. Cost of building this side is 5x. Cost of building this side, let's think about that. Well, let's see. Well, let's just give this side length a name like W. Okay, so the length of this side is W. So, I mean, I guess it would be 9W if in that case. 9W, if you have a quantity, you don't know what it is, you can just give it a name. So we can just write down a formula for cost, even if it involves more than one variable. At least we have something written down. Cost is equal to 5x plus 5x, hey, that's 10x, plus 9w plus 9w, that's 18w. But we need a formula for cost in terms of just x. So how do we relate w and x together? Well, let's think. The length of this side is x, right? The length of that side is x, so let's think x and w, but they should multiply together to make 100. Ooh, there we go. We have an equation that relates x and w. So it'd be nice if we could replace w with an expression in x. So let's solve this equation right here for w. Divide both sides by x. We get 100 divided by x is equal to w. We can replace w here with 100 over x. So we get 10x plus 18 times 100 divided by x. There's our cost function that we'd like to take a derivative of in order to find the minimum cost. So to do so, let's see, the derivative of this part is just 10, that's nice. This part right here, this is like, so this is 1800 times x to the negative 1. So that becomes, using the power rule, negative, and then, so negative 1 comes out front times the 1800. So negative 1800 times x to the negative 2. And that's going to be equal to the first derivative. All right. So we want to know where this is equal to 0 or undefined for critical points, at least but wait a minute. We don't want x to be 0 anyway, so really that rules that out. We're only looking for positive x, so really we just want to find a value for x that's positive. That's a critical point. X to the negative 2, we can't put 0 into that because that's really negative 1800 over x squared, right? So really, that's a place where this would be undefined, but we aren't interested in that guy because it doesn't make sense in the situation. So, and in fact, looking at this x squared thing from symmetry, it doesn't even have a sign change there. So the derivative doesn't change from positive, negative, or anything. So you were just looking for x values that are positive here. So let's take a look at this for the and figure out where this is equal to 0 for a positive x value. What we can do is we can add fractions and then get this in factored fraction form, set it equal to 0. So we can multiply this fraction top and bottom by x squared. So we have a common denominator. Then we have 10x squared minus 1800 on the top over x squared is equal to 0. A fraction is equal to 0 when its numerator is 0. All right, as long as the denominator is non-zero, but we're assuming x is positive anyway, so really that's okay. All right, so taking a look at this and at this equation, we can divide this equation both sides by 10. So we're left with x squared minus 180 is equal to, so x squared minus 180 is equal to 0. So we get x squared is equal to 180. And then x would be equal to plus or minus the square root of 180, but we're not interested in the negative solution. We're only interested in the positive one, positive square root of 180. And I suppose if you want to, you could work through simplifying that down a little bit more. I mean, 18 itself is 9 times 2. And then you have 18 times 10, so it's like 9 times 2 times 2 times 5. And then, because 2 times 5 is 10. So notice you have a square, oh, look, you have a square with a 9 and a square with a 2, or 36, right? So that's 36 times 5, and that you're square rooting. So it really looks like 6 root 5. So you could simplify it that way if you wanted to. As we go along. So doing a sign analysis, but doing a full sign analysis on this guy, we really do need to use all the critical values. I mean, this guy is probably going to be the winner. It makes most sense in our situation, but if we want to do a sign analysis of this derivative, we really need all the critical points and expand the domain to everything. So really, look, it's undefined at 0, and you have plus or minus 6 root 5. So really you have like 6 root 5 minus 6 root 5, and you have 0 coming from x squared. If you want a sign determining polynomial, this x squared would come up to the top. And so you'd have, and you're thinking about leading term, you'd have x squared times 10x squared. That'd be like x to the positive x to the fourth, and behavior up. And so you'd start up, and then you would end, and you would end up, and it looks like you would hit at least these have a multiplicity of 1 apiece, because it's like x minus 1 times x minus the other plus or minus the other one. So, and then with the x squared, you're going to have a bounce at 0, but these guys will shoot through. These ones will shoot through, bouncy, shoot through. So with this sign analysis, the original function looks like it's increasing here, and then it's decreasing. And it decreases all the way to there, and then it's the derivative is positive, so it's increasing from there. Realize this is derivative sign. Sign of the derivative. Sign of the derivative, derivative, sign of the derivative. So increasing, then decreasing, then increasing. It looks like the minimum happens right there, which guarantees that our point that we found is actually a minimum. Now that was a full sign analysis of that first derivative. You could think of that as being kind of like a version of a first derivative test. Now a second derivative test probably would have been simpler in this case. Why in the world did we do it this way? Just to have some fun. All right, but anyways, let's do second derivative test as well. Second derivative, we take the second derivative, that constant will go away, this negative 2 comes down, power rule, and we would be left with positive 3600 x to the negative 3. Now notice we're plugging in a positive number, which means the second derivative is actually going to be positive at that point, meaning we're concave up. So think concave up, but with a 0 slope. that's a minimum, which is what we wanted to guarantee anyway. So, okay, so all that work to just determine that x equals 6 root 5 gives us a minimum. Great. Okay, so this side length should be 6 root 5 in order to have a minimum cost. What should this side length be? Well, remember, 6 root 5 is a value of x, and that times w will be equal to 100. So we can figure out what w is by dividing both sides by 6 root 5. And then you just have what w should be, which, so w will be equal to 100 over 6 root 5. And I guess in this fraction you could reduce a couple things. You could just share a common factor of 2. You could divide top and bottom by 2, so 50 over 3 root 5. And for all intents and purposes, I'm okay with the square root being in the denominator. But for those that like to change it out, you could multiply top and bottom by root 5. And then you would be left with 5 times 5, so in the denominator, so which just give you, or square root of 5 times square root of 5, which just gives you 5. And I'll just leave it as 3 times 5, 50 root 5. Why did I do that? Just so we could see how that cancels. That 50 and 5 can reduce to 10. So it really looks like w is equal to 10 root 5 over 3. So you could write it that way as well, and that's fine. Really, 50 over 3 root 5 is okay. I mean, I guess if you multiply top and bottom by square root and get rid of the square roots, there is an additional cancellation that we got, which was kind of reduction that we got, which was kind of nice, I suppose. But anyways, we get what our dimensions are, this guy and that guy, and we can double check our algebra if we really wanted to, make sure it worked right. So just think, if we really multiply 6 root 5 by that, let's see, root 5 and root 5 would give us 5. And then you think, okay, 5. And then 6 times 10 divided by 3, and that gives us 20 times 500. Okay, so it looks right. So we got our w, we got our x, we did our sign analysis in kind of a fun way. If you want it, what I was using was a sign determining polynomial. I have a video on that, so you can look that up in my channel. And to see kind of what in the world I was doing. But if you want to ignore it completely, go ahead, it's fine, because there's a second derivative test right here. We're just checking concavity right at that point. So I hope you can glean something from this video. Thanks for watching.